Hello sir, myself Karan Kumar Kumbhani, enrollment number 066. The topic of presentation is OFDM, Orthogonal Frequency Division Multiplexing. First of all, we should know that what is an FDM, Frequency Division Multiplexing. FDM has been used for a long time to carry more than one signal over a telephone line. FDM divides the channel bandwidth into a subchannel and transmit multiple relatively low rate signal by carrying each signal on a separate carrier frequency to ensure that the signal of one subchannel did not overlap with the signal from an adjacent one. Some guard bandwidth was left between the different subchannels. OFDM, Orthogonal Frequency Division Multiplexing. In order to solve the bandwidth efficiency problem, orthogonal frequency division multiplexing was proposed. Where the different carriers are orthogonal to each other with OFDM, it is possible to have overlapping subchannel in the frequency domain, thus increasing the transmission rate. This carrier spacing provides optimal spectrum efficiency. Today, OFDM has grown to be the most popular communication system in the high-speed communication. OFDM is become the chosen modulation technique for the wireless communication. OFDM can provide large data rates with sufficient robustness to radio channel impairments. This is the example of OFDM. In the first example, there is one tap and the shower. The tap is similar to the FDM and the shower is similar to the OFDM. The water flow is coming from the tap is big stream, and in the shower the water flow is in the little bit or so we can say subcarrier. If I put my hand on the hand in the mouth of the tap, the water flow is stop. Meanwhile, in the other hand, I put my hand on the shower, so some portion of water continuously. The second example of OFDM is if we transfer and shipment. So we have to choose. First, we can hire one big truck or smaller one, a bunch of smaller one truck. So in the smaller one, if the accidentally of one of the truck, we lost only 1/4 data. This is the OFDM is a special case of FDM. The first figure shows the FDM signal, and the others and the second one is the OFDM signal one, where the signal or a subcarrier overlapping on each other to so it is saving the bandwidth. This is an example of OFDM using 4 subcarrier. This figure shows the bit rate for the modulating by the 4 subcarrier. Here in the first figure, the modulated signal is modulated by the 1 Hz. In the second, the subcarrier is modulated by the 2 Hz. In the third subcarrier, the modulated by the 3 Hz, and the fourth subcarrier is modulated by the 4th Hz. OFDM signal in the frequency and time domain. The first and second figure is showing the time and frequency domains OFDM signal, and the third signal is the parallel to serial conversation, which is also known as the IFFT. Generated OFDM signal. In the input, we give the signal to serial to parallel conversation and then IFFT, and we got an output from FFT and parallel to serial conversation. The second figure is showing the OFDM generated signal. Fading. In attraction of OFDM is mainly because of its way to handling the multipath interference at the receiver. Multipath phenomenon generate two effects. First, frequency selective fading, and the second, intersymbol interference ISI. The flatness perceived by the narrow band channel overcome the frequency selective fading. On the other hand, modulating symbol at the very low rate makes the symbol much longer than channel impulse response and hence reduce the ISM. Used for suitable error correcting codes provide more robustness against the frequency selective fading. The insertion of extra guard interval between consecutive OFDM symbol can reduce the effect of ISI even more. A definition of fading. The path from the transmitter to receiver either has reflection or obstruction, we can get a fading effect. In this case, the signal reaches the receiver from many different routes, each a copy of the original. Each of these rays has a slightly different delay and a slightly different gain. The time delay result in phase shift which added to main signal component causes the signal to be degraded. Fading. In the first figure shows the signal we want to send and the channel frequency response as well matched. The second figure showing a fading channel has frequency that do not allow anything to pass. Data is lost sporadically. And the third figure is showing with OFDM where we have many little subcarriers. Only a small subset of the data is lost due to the fading. OFDM signal offer an advantage in the channel that has a frequency selective fading response. Instead of the whole symbol being knocked out, we lost a small subset of the bits. With proper coding, this can be recovered. The BER performance of an OFDM signal in the fading channel is much better than the performance of QPSK or FDM, which is a signal carried by a wideband signal. Guard time and the cyclic extension. Suppose we drive in the rain and the first front car is splashing a bunch of water on us. So we increase the distance between us and the front car. The same thing is doing in the guard time and the cycling extension. Guard time and the cycling extension. The PSK symbol and its delay version. Move the symbol back to the arriving delay signal preferred out in the gray region. No interference to the next symbol. We just extend the symbol, then the front of the symbol, which is important to us since it allows figure out what the phase of the symbol is. Now corrupted by this place, we move the symbol back and just put in convenient filler in this area. Then not only we have a continuous signal but one that can be get corrupted. We don't care since we will just cut it out anyway before demodulating. Cyclic prefix is a copy of back of the symbol we added to the front of the symbol. Slide the symbol to start at the edge of a delay spread time and then fill the guard space with a copy of a turn out to be a tail end of the symbol. We will be extending the symbol so it is a 1.25 time as long. To do this, copy the back of the symbol and glue it in the front. We can add cyclic prefix just one to the composite OFDM signal. The prefix is anywhere from the 10% to 25% of the symbol in time. The addition of the cyclic prefix which migrated the effect of the link fading and inter-symbol interference increase the bandwidth. This figure shows the OFDM signal. In the OFDM signal, the cycle is going to only one time. Windowing. OFDM signal consists of a number of unfiltered QM subcarriers. As a result, the out of the band spectrum decreases rather slowly. According to the sciencey function, spectra of 16, 64 and 256 subcarriers are plotted for a large number of subcarriers. The spectrum goes down more rapidly in the beginning, which is caused by the fact that the side lobes are closer together. To make the spectrum go down rapidly, windowing can be applied to the individual OFDM symbols. Windowing can an OFDM symbol make the amplitude go smoothly to the zero at the symbol boundaries. This is the equation of windowing, where Wt equals to 0.5 plus 0.5 cos pi plus t phi into beta ts, where t is belongs to 0 to beta ts. Here t is belongs to beta ts into 2ts. So put the value into the first equation, so we can get 0.5 plus 0.5 cos into t minus ts pi beta ts, where t is belongs to t into 1 plus beta ts. Here ts is the symbol interval, which is shorter than the total symbol duration because we allow adjacent symbol to partially overlap in the roll of region. The practical OFDM signal is generated as follow. First, NC input QM values are padded with the 0 to get an input symbol that are used to calculate an IFD. The last T prefix sample of the IFD output are inserted at the start of the OFDM symbol, and the first T post sample are appended at the end. The OFDM symbol is then added to the output of the previous OFDM symbol with a delay Ts, such that there is no overlap region of beta Ts, where beta is the roll of character of the raised cosine window. Instead of windowing, it is also possible to use convolutional filter technique to reduce the out of the band spectrum. Windowing and filtering are dual technique. Multiplying of an OFDM signal by an windowing means the spectrum is going to be a convolution of the spectrum of the windowing function with asset impulse a function at the subcarrier frequencies. When filter is applied, a convolution is done in the time domain and the OFDM spectrum is multiplied by the frequency response of the filter. Digital filter techniques are more complex to implement than that windowing. Choice of OFDM. When we design the OFDM system, the parameters of are considerations such as the first number of subcarriers, guard time, symbol duration, subcarrier spacing, modulation type per subcarriers. The choice of parameter is influenced by the system requirements. Usually there are three main requirements to start with. First, available bandwidth, second, required bit rate, and the third, tolerable delayed spread. The delayed spread is directly detect the guard time. As a rule, the guard time should be about 2 to 4 times the root mean square delayed spread. This value depend on the type coding and the QM modulation. Higher order QM is more sensitive to ISI and ICI than QPSK, while heavier coding obviously reduce the sensitivity to the such interference. Now that the guard time has been set, the symbol duration can be fixed. To minimize the signal to noise ratio in SNR ROS can by the guard time. It is desirable to have the symbol in duration much larger than the guard time. Larger symbol duration means more subcarriers with smaller subcarrier spacing, a larger implementation complexity, and the more sensitivity to the phase noise. Practically design choice to it to make the symbol duration at least 5 times to the guard time. The number of subcarriers follows directly as the required minus 3 dB bandwidth divided by the subcarrier spacing, which is the inverse of the symbol duration less the guard time. Another way to determine the subcarrier is required bit rate divided by the bit rate per subcarriers. The bit rate per subcarriers is defined by the modulation type, coding rate, and the symbol rate. Thank you, sir.